is cognitive scientist, and you know better. But I am artificial intelligence researcher, so maybe I can tell a little bit what is artificial intelligence, and here I feel more comfortable to even come up with something. And when we talk about artificial intelligence, we need to talk about two entities. One entity is some environment, some world. So this is something big that there we have some agents. It could be a robot. We can think of a robot. We can think of a system. It could be virtual environment, but there are more or less two actors. And our AI system, our robot, interacts with this environment. Okay. So when we have some interaction, it means that there is some information flowing from the environment to the system. It processes it and then makes some decisions, takes some actions. And when we talk about information, we live in digital era, so we have some stream of bits flowing to the system, right? Some information, right? It could be in the simplest case, and it is something worth to keep in mind. It could be, for instance, that we have a robot with some camera. It takes some photos, and it needs to make some decision. All right, so this is the general framework of artificial intelligence. It's still vague. What is artificial intelligence? But this is our starting point, all right? And if we think about more specific aspects, so we have information, right, flowing from the environment, from the surrounding, and the system needs to process this information. It needs to store this information. It needs to transmit this information, for instance, for communication purposes. And of course, it needs to make some decisions. And altogether, to achieve this, let's say, goals in some sense, we need learning. We need to know how to represent knowledge internally. We need some models in general. Okay, so this is more or less pretty vague definition of artificial intelligence. It consists of many different aspects, and we should take care of them. But of course, still we need to know how to formalize the problem of artificial intelligence, right? And so here, stay with me. There will be a little bit of mathematics, but I hope that you will follow it. And if you don't worry. So just try to understand what we are talking about in general. So very quick recap. I talk all the time about information, so it would be nice to know what is information, right? And in 30s, 40s, there was a person called Claude Shannon, and he made a huge progress in our understanding of what is information, and he coined this term properly. So let's say that we have some random source of data. It could be about images, some images that some camera is taking, and we have these images coming in. This is the source of data. Then we can actually quantify how uncertain is this source of data, okay? And this is extremely important because in the very beginning, when I tell you there is some data coming in, it's hard to say anything about it. But when we can quantify it, we can calculate some number, it's very good for us because then we can play with this number, okay? And we can understand something through this number. And entropy actually serves this purpose. And the entropy tells us how uncertain is this source of data. In other words, if you get one single image and it comes all the time to you, so you can say, well, this source of data is very certain because I always see the same image, right? But when you get a lot of different images, and they are all the time changing, and there is something new, then you are very uncertain, or this source is very uncertain, right? Because there is everything popping up, and this is all the time something different. And this is what this entropy tells us. And the entropy is just you take the P of X is a probability of observing some value X, and log of P of X is the logarithm of probability of that, okay? And as I explained to you, and I hope it makes, intuitively, it makes sense. So we get the maximum entropy, the highest possible uncertainty, when every single X, every single, for instance, image has exactly the same probability. So it means that all images are possible to observe, all kinds of these images, right? Including noise and so on. So this is what we say, that the entropy is maximum when everything is equiprobable. However, the other extreme is when we have one single image that has probability 1. It means that it will all the time occur. Nothing else will occur. For instance, my face like right now. And now you see all the time this face, it's frozen. So this is entropy is minimum. And it's 0 for discrete cases. All right, so this is information. This is what Claude Shannon told us. And he helped us to quantify something, you know, etheric like information, right? So he pinned it down and he said, this is how we can measure information actually. And the second thing that he showed, and this was a milestone, is that the optimal message length. So when we send something, and I want to send some message to you, I'm using language and this slides. So the optimal message length is more or less, we can think that this is the entropy of this data, source of data, okay? So that's why this is so important. So now you see that why I'm talking about this information, because it's artificial intelligence. It's about processing information, transmitting information, storing information. So we have to have some kind of tool that we know how to calculate what is the message length that I need to communicate. Okay, this is the entropy. Another very useful concept is, of course, when we have two sources of data and we have the joint entropy of two random variables or random sources of data, right? So we can now say that we have X and Y, and X is, for instance, image, and Y is some action that the agent, the robot, the AI system should take, right? So then we can calculate by observing the reality what will happen if the robot will, for given image, will make some action, right? And so this is the joint entropy, and there is also the conditional entropy with a slight difference, that we need to average over all possible states of images and actions. And we calculate it with respect to logarithm of the conditional distribution. So in other words, what is the probability for given X that I will take some action Y, okay? So this is the conditional entropy. It tells us what is the uncertainty of my action for given observed X. And then I average over all the possible actions and images. All right, so this is the conditional entropy. And now the last slide that is introductory, it's mutual information. So mutual information between two random sources of data tells us how much information is shared by the two sources. Or in other words, how much knowing one source reduces uncertainty about the other source. All right, so this is actually very crucial, and this will be the core of this this short talk, because mutual information tells us something very important. When I know, for instance, what is the image, so how much information is uncertainty is decreased for given actions, right? So for instance, if a robot sees mountains, maybe it will start climbing. And then when it sees, I don't know, water, it will not step in. It will stay away. So this is the feeling about the mutual information, right? So it, again, quantifies for given axis what kind of Ys we can expect. And when it shrinks this probability, so it means that they share some information together. All right, So now we are ready to say something about AI, really AI. So let's say that we have these two sources of randomness, some images, some decisions, something that I talk all the time right now. And we have some model. Let's say that we have whatever, it could be neural network, it could be any other model that it could be a brain, like in our heads. There is some model, and this is some kind of, broadly speaking, a representation of some worlds or our worlds. And what is the goal now of this entity, learning entity? So the goal is to actually maximize the mutual information between all possible states of the world and the model. And if the model will maximize this mutual information, what does it mean? It means that once my model is trained properly, so it will know what will happen. Okay, so they will share maximal information between each other. Okay, so far so good. I hope this is understandable, because this is extremely important slide. And why? Because if we say that actually what the agent wants to do is to maximize mutual information, it says that we have this part, this entropy of the world, and this is the entropy of the world, and the model has no influence on that. It happens. It's almost like, you know, Buddhism. Just don't care about the outside world. Focus on yourself. And the second part, the second component here is that what is the entropy, conditional entropy of states of the world for given model. And we want to find such model that will actually minimize this. So we want to maximize the whole thing, but because this is a minus, so we want to minimize this entropy. We minimize uncertainty. This is the real goal of AI. And sorry, this is another a bit more mathematical term, but we need that to actually say something about generative models. So we want to minimize uncertainty of the world. And so I just written down the definition of this conditional entropy. And we have two components. There is this model for decision making, and there is this model for understanding the world, what I call it. Okay, so this is what is the probability of observing images in the world. Okay, so we have these now two models, and this is what AI should focus on during learning: how to make decisions, but also how to understand the world. And currently, the bulk of the work in AI is focused on decision making only. Okay, and that's fine. We have amazing papers. For instance, we can have a model, a neural network, for instance, that is trained on recognizing images. And here we have a cat, and okay, the probability of a cat is the highest. So the agent understands what's going on. But a lot of people show that actually, if you add even a little bit of noise, suddenly you are failing completely. And instead of saying that there is a cat, a system, AI system, fails. All right. And why it happens? So it happens because we don't know what is the P of X, and we don't know how to properly evaluate the state of the world. Okay. And here is a simpler example. And we have some two data clustered together, and there is new data point with this big bold X. And let's say that we train a model, and this is really trained. I wrote a piece of code that implemented some naive Bayes or something like that. And it learns this decision boundary, right? So whatever is on the left, it's orange. Whatever is on the right, it's blue. So of course, now, if you ask AI system, what is X? And this X is far away from the decision boundary. So it will say, well, with high probability, this is blue. So this is this class because it is further away from the orange one, right? But this is not necessarily true, because what we should do, we should also calculate the probability of observing X in this space, right? And as you can see, this X is actually far away from the cluster of orange, good, but also far away from blue. cluster, right? So it means that the probability of observing this X is actually very, very low, okay? So it's not consistent with the data we observed so far. So that's why the decision altogether by multiplying these two probabilities should be low. So the state of this world is something off. There's something off, something weird, okay? So that's why we need this generative perspective. We need to learn also this P of X, okay? The probability of the world, let's say. And how we can learn it? So there's a lot of different models. There are autoregressive models, flow-based models, latent variable models like GANs, generative adversarial networks, VAEs, variational autoencoders, and many more, but these are the ones that can actually learn P of X. And because, of course, this talk is almost over, so you know, I will not go into details, but there's a plethora of different generative models. And there's a very active research line, and it is applied to many different fields, like there are standards AI fields like text analysis, image analysis, audio analysis, but also to, you know, graph analysis, to generate molecules that have some very specific properties for visual screening, for instance. In reinforcement learning, active learning, where an agent tries to, you know, dream about the future, and also medical data, and so on, so on. There's basically everywhere, because this is how we human beings also work. We not necessarily take some image and we make a decision. We try to figure out what are the connections in the world, what could happen, so we can actually dream about something. What will happen if I make this step? It will be good or bad, right? And a takeaway message from this short talk is that decision-making model is perfectly fine. I'm not saying that there is something wrong with that, but it's just simply not enough to use to create, let's say, true AI, whatever it means. But I hope that we now agree what is a true AI. To have this true AI, we need to know, we need to understand the reality. We need to properly quantify uncertainty to get a system that will be really mimicking human beings, for instance, right? Or animals, some intelligence that it's really artificial. Okay, if you are interested in going deeper, so I have a series of blog posts on this very specific models. So please don't hesitate to visit this blog. Thank you very much.
Thank you, Jakub, for this amazing talk. I have a lot of questions on my side, and I'd love to ask them, but first, I guess that we will allow our attendees to ask questions. So I see a raised hand from Magda Esch, and Magda, you can ask the question.
Hello, great talk.
Hello.
Thank you very much. I'm just a stupid biologist, but I got it, I hope. So good job.
Perfect.
What I didn't get, and I have a question. So you mentioned at some point that the optimal message length is more or less equal to entropy.
Right. Which
to me is a bit counterintuitive, because I would assume that the longer the message, the entropy should be smaller.
No, in this case. So it's it should be read in different ways. So when you have, it's easier to explain in using some language.
Yeah.
So it says that if we want to communicate, we have words and symbols, right? Even simpler. And then imagine that there is, let's say, English. English has, and we have a dictionary, we have this all sentences, grammar, all this stuff.
Mm-hmm.
And this is P of X.
Yeah.
This is X is some sentence or whatever. Yeah. And then how you can build these sentences. So some sentences, and of course now you can start building them using very random procedure, like just simply select some words and glue them together.
The longer your sentence, the more permutations you could have of all the possible words to be used in such sentence.
This is true, but also you can say that if I want to communicate that the weather is bad in Amsterdam, which is unfortunately true, so then this is the probability of this sentence, right? Is highest. I can add some other adverbs and verb or something like that. But to in some sense to transmit the message to you, it's actually enough to say this. And this is in some sense the probability of this sentence. It's more or less equivalent to the length of the message if I turn it into bits.
Okay, so you mean that the simpler message is better? So
in general, yes. So it was even this very nice thought experiment from Shannon when he said, well, and for actually Slavic people, Polish people, so removing all this D, A, and so on, it's of course something like redundant. And he said the same. So he said, wow, actually, if we remove all these articles, we still get what is the message. We lose a little bit of information, right? Sometimes, but it will be not ambiguous. You will get what is going on in the sentence. So yes, this is in some sense you can say the shorter message is better, and probably it will fit the entropy of the world and of the state that you want to communicate.
Yeah. Okay, thanks a lot.
Thank you.
Okay, so I guess that, we have a question from Evelina as well.
Hi, Jakub. Hi. Thank you for your amazing talk. I'm just a stupid mathematician again. This is how we introduce ourselves here. So, sorry, Magda, but I think that you asked a very good question, and
very good.
I have one more to add to that. So just let me lower my hand now. So I was wondering about this relative entropy that you called it differently, but the entropy that measures some sort of distance between the world and what you really. Can you say something more quantitatively, other than okay, this is a good fit to the world's state? Can you have some rates of convergence for your scheme? Do you actually get?
Yeah, so this is of course an amazing question, and this goes maybe beyond a stupid AI person I am, but now very seriously speaking is so it's only the touching upon the problem, to be honest. So this representation, because of course we don't have, for instance, the real distribution of P of X and M, so we need to anyway approximate it. Okay. So this is the first thing. And second, of course, now this is a very static scenario also. So there is more suitable would be some kind of dynamic. But even in this static scenario, there is actually quite a lot of work on using exactly information theory to prove some upper bounds on, for instance, generalization error or something like that. So maybe it's not exactly some convergence rate, but in some sense, you know, for instance, if the distribution of states of the world are very complicated, so and our entropy is really high, so then generalization will be, for instance, more difficult, which makes intuitively sense. Sure. But it is quantified that there is some upper bound, for instance, on making some mistakes in the world. Mm-hmm. But to be honest, this is still ongoing research. The information theory is really used in many aspects of AI. You know, in deep learning, there is a lot of work. I even saw a paper on showing that, you know, stochastic gradient descent, an optimization procedure, that it also has some some nice properties actually, and that it allows to generalize. So yeah, I think it's to me it's an amazing tool, and it's an amazing language, and I think that every AI person should actually learn information theory in depth, because this is actually about yeah, artificial intelligence. And even in the very first paper, so there was Nyquist, and then there was Wheatley, and then there was Shannon, and they published almost something like year by year or something like that. And Nyquist actually first in his paper he called intelligence what we know now as information. And then it was Wheatley that said information, and he considered only uniform distributions. And then Shannon said, hey, actually we can use any distribution. It doesn't need to be only uniform, and that's the information theory. But sorry, I diverged a little bit. But so yeah, so this is something definite. There's a lot of work that uses information theory in different aspects of maybe machine learning, AI. But still, I think that we need some. Maybe we can even. I tried to Google for it to see whether I'm not saying some nonsense, but I think that this is very good language, information theory, to explain what is going on in AI in general. And I think that I saw even papers in biology that actually they try to see whether we can use information theory at the cell level. And in some cases, they even did some crazy experiments, and they proved that actually cells, they also communicate, and you can also quantify it using information theory.
If I can exactly mention something on this, yes. So I mean, not me personally, but we try to do this, and of course, cells communicate, sending proteins and other things to each other.
Yes.
And there's a lot of models that try to also model the noise in such communication, and the noise of like stochastic gene expression and things like that. So a lot of information theory starts being used there, but it's still not very mainstream, because biologists are generally a bit afraid of computer science, but it's getting there.
And also it's, I think, very hard to actually measure something, right? So it's to construct a good experiment, I think it's also difficult.
Exactly. So we usually measure things but much more qualitatively than quantitatively. And of course, quantitative information is essential here.
Yes. And a very fun fact, because I'm actually reading a biography of Claude Shannon. So he did his PhD on genetic expressions, actually.
Oh, wow.
So it's very funny that he did his PhD. He was super unhappy with the topic, but I think it gave him a lot of thoughts what to do.
Yeah, every biologist is unhappy at some point.
Yes. Yes, I think it might be true. So Evelyn, I hope that you are satisfied to some extent with this.
Yes, I mean, I just wanted to hear how far do we have to stretch. I mean, so it was a bit, you know, it was that and question really, because on one hand, you know, we have this rigor that you're looking for, right? We have this optimal transportation techniques that would allow you to approximate the microscopic models or precision that you're looking for, with the macroscopic, more mathematically treatable one. But it looks like, you know, this passage from micro to macro is essential. I'm going to talk about it. But we are bounded to very simple settings that you probably will not find applicable, right? Because in your set of possible entropies, and we don't really have that much of information about what could be the steady states and so on. And this, of course, then generates further problems in convergence mechanisms, and sort of restricts us really to what we can prove. But I think that there is what I see from my, backyard is that really a lot of people in my community also try to put some rigor into that directions, even in PDE community, so it's not only the statistical mechanics or the quantum information theory, but also people working in macroscopic equations that should give you more general picture. So something like image processing, right? This would be very close to what we were presenting today. And there we have some mathematical rigor, not only additional results.
Yeah.
Okay, thank you again for this talk. It was really great. Thanks.
Thank you, and it's brilliant also what you said, because in fact, so it's very nice what I said, and please remember that it was nice. But of course, calculating entropy is impossible, right? Especially for a little bit more challenging tasks than having Gaussian distribution. Right. So we and in AI people actually use a lot of also heavy math, of course, optimal transport, and all kind of crazy ideas that mathematicians come up with. We use in AI, and we try to use them and to make them applicable. Right. So it's very often there is a typical paper in AI that it has a beautiful theory, and then it boils down to some tricks to make it applicable, like in code and so on. Yes, so basically the whole idea, everyone working on information theory in AI or using information theory, it is about having approximations, lower upper bounds, anything that makes it applicable. So we definitely, it's always we are looking for mathematicians and their papers, and the first person who translates mathematical paper to machine learning paper, it's always something like cited like crazy, and everyone is excited. So it's definitely it's a beautiful field actually.
Thank you so much, Jakub, for your talk.